Hey everyone, and welcome to another deep dive. This time we'll be exploring something that's all around us, but we may not always notice it.
Sounds intriguing.
It's motion, specifically the kind that repeats itself over and over.
Oh, you mean periodic motion.
Exactly. And we're going to focus on one special type, simple harmonic motion.
The foundation of so many things in the universe.
You got it. We'll unravel what makes SHM so special and why it's everywhere, from the swing of a pendulum to the vibrations of a guitar string.
I'm ready to dive in. Where should we start?
Well, first things first, let's define what makes motion periodic. What do you say?
Okay, so think about anything that repeats itself in a cycle. That's periodic motion.
Okay.
Like the Earth going around the sun, a clock's hands moving, even our heartbeats.
Makes sense. They all have a specific time period, right? The same time to complete one cycle.
That's it. Now let's bring in oscillatory motion. It's a special kind of periodic motion.
Okay, I'm listening.
It's where an object moves back and forth, but always around a fixed point, like a pendulum swinging.
Right. It always comes back to that center point.
Exactly. Or think of a weight on a spring bouncing up and down. That's another classic example.
Oh, yeah. Or even the vibrations in our phones. Those are super fast oscillations, aren't they?
Exactly. They're tiny and incredibly quick.
So we have periodic motion, and under that umbrella is oscillatory motion, which can be slow and big like a pendulum or super fast and tiny like vibrations.
You got it. And now, let's zero in on simple harmonic motion, or SHM. It's the simplest kind of oscillatory motion.
What makes it so simple, or harmonic for that matter?
Well, it's the relationship between how far an object is moved from its rest point and the force pulling it back.
There's a storing force, right?
Yes. In SHM, the restoring force is always proportional to the displacement. So the more you stretch or compress something, the stronger that pullback force gets.
I see. So, like with a spring, if you pull it further down, it wants to snap back harder.
Exactly. And this is true for both linear SHM, where the motion is along a straight line, like with our spring, and angular SHM.
Angular SHM, what's that?
That's when the motion is a rotation, like a pendulum swinging back and forth. Think of it as a back and forth around a fixed axis.
Ah, okay. So even though the motion's different, they both involve a restoring force that's proportional to how far the object has moved.
Precisely. It's this special relationship that makes the motion harmonic.
Okay, I'm starting to get the picture. Now, are there any special terms we need to know to really grasp SHM? It seems like there might be a lot of vocabulary involved.
You're right, there are some key terms. But don't worry, they're not too complicated.
All right, hit me with them.
Well, let's start with mean position. It's the stable point where the object would naturally rest if it weren't oscillating.
So for our string, it's when the spring is just hanging there, not stretched or compressed.
Yes, that's its happy place, its home base.
Okay, that makes sense. What about amplitude?
Amplitude measures how far the object swings away from that mean position. The bigger the swing, the larger the amplitude.
So if I give that spring a big tug, it'll have a large amplitude, but a little nudge would be a small amplitude.
You got it. Now let's talk about time period and frequency. They're closely related.
Okay, I'm ready.
Time period is simply the time it takes for one complete cycle of the motion. For a spring, it's the time from the top of its bounce all the way down and back up to the top again.
And frequency tells us how many of those cycles happen in 1 second.
Exactly. So if it bounces up and down 5 times in a second, that's a frequency of 5 cycles per second.
Okay, I think I'm getting that. But what about phase? That one always seems a bit tricky.
Think of phase as a way to pinpoint where the object is in its cycle at any given moment.
Like a snapshot of its position and direction.
Exactly. It tells us if it's on its way up, on its way down, or at one of its extremes.
Oh, I see. So it's not just about where it is, but also where it's headed.
Precisely.
Yeah.
And there's one more. Angular frequency.
Ooh, that sounds a little intimidating.
It's simpler than it sounds. It basically tells us how fast the phase is changing or how quickly the oscillations are happening.
So it's like the speed of the oscillation.
You got it.
Wow, we've covered a lot of ground here. From defining SHM to learning all these new terms, I feel like I'm starting to speak the language of simple harmonic motion.
That's great to hear. And to really solidify these concepts, let's visualize SHM. Have you ever thought of it as a projection of circular motion?
A projection. I'm not sure I follow.
Imagine a point moving around a circle at a constant speed. Now, if you shine a light on that point and look at its shadow on a flat surface, you'll see something interesting.
Okay, I'm picturing it. What happens to the shadow?
The shadow moves back and forth, and you know what? It's moving in perfect SHM.
Wow, really? So that simple back and forth motion we see in SHM is actually like a glimpse into something moving in a circle.
Exactly. And the speed of that circular motion directly relates to the frequency of the SHM we observe. It's a beautiful connection.
That is pretty cool. I'm starting to see how seemingly different types of motion can be connected.
It's all about perspective. And speaking of connections, let's talk about energy and SHM. It seems like there's a lot of back and forth there as well.
Yeah, like a constant exchange between motion and position.
You're spot on. In SHM, we see this interplay between kinetic energy, the energy of motion, and potential energy, the energy of position.
So like a trade-off, right?
Exactly. Let's think about our spring again. When that weight is at the very top or bottom of its bounce, it's not moving for a split second. All its energy is stored as potential energy.
Because of its position, right? The spring is either stretched or compressed.
Exactly. It's like that moment at the top of a swing when you're momentarily still before swinging back down. It's all potential energy waiting to be released.
I love that analogy. So what happens as the weight starts moving back toward the middle point?
That potential energy gets converted into kinetic energy. At the middle point, it's moving at its fastest, so kinetic energy is at its peak and potential energy is zero.
Then as it moves towards the other end, that kinetic energy gets converted back into potential energy, and the cycle starts all over again.
You got it. It's a constant dance between these two forms of energy. And what's amazing is that the total energy in the system stays constant throughout this whole process.
Wow, that's pretty neat. So even in something as basic as a spring bouncing, there's this intricate energy interplay happening.
You see, even seemingly simple things can reveal amazing complexities when we take a closer look.
Absolutely. Okay, now I'm curious to see how all this SHM theory plays out in the real world. Are you ready to move beyond our trusty spring?
Of course, there's a whole world of SHM examples just waiting to be explored.
Okay, lead the way. What's our first stop on this real-world tour of SHM?
Let's start with a classic example, the simple pendulum. You know, that image of a weight swinging back and forth on a string.
Oh yeah, like the pendulum in a grandfather clock. It's mesmerizing to watch.
It really is, and it beautifully demonstrates the principles of SHM. The swing of a pendulum is determined by just a couple of things: gravity and the length of the string.
So a longer string means a slower swing.
You got it. The time period of a simple pendulum, which is the time it takes for one complete swing, is directly proportional to the square root of its length.
Okay, that makes sense. And what about gravity?
Well, gravity plays its part too. Imagine a pendulum on the moon, where gravity is weaker. It would swing much slower than an identical pendulum here on Earth.
That's fascinating. So it's like a delicate balance between gravity pulling it down and the length of the string affecting how far it swings.
Exactly. And if we keep those swing angles small, the motion of the pendulum can be very accurately described as SHM.
So even though it's not moving along a straight line like the spring, it still follows the rules of SHM.
Precisely. That restoring force pulling it back towards the center is still proportional to its displacement, just like with our spring.
It's amazing how those principles apply even in different types of motion.
Yeah.
Now, you mentioned something about a seconds pendulum earlier. What's that all about?
A seconds pendulum is a special type of pendulum designed to have a time period of exactly 2 seconds. That means it takes 1 second to swing to one side and another second to swing back.
Ah, so it's literally measuring out seconds with each swing.
Exactly. And this precise timing was crucial in the history of timekeeping. Before quartz clocks and atomic clocks, pendulum clocks were the most accurate way to measure time.
It's incredible to think that something as simple as a swinging weight could be the foundation of our ability to track time with such precision.
It all comes back to the power of understanding SHM. But let's move on from the simplicity of the simple pendulum to its more complex cousin, the compound pendulum.
Compound pendulum. So if a simple pendulum is like a solo dancer, is a compound pendulum a whole dance troupe?
That's a great analogy. A compound pendulum is any rigid object that can swing or rotate around a fixed axis. Think of a swinging door, a metronome clicking back and forth, or even a child swinging on a swing set. They're all compound pendulums in action.
So it's not just a point mass on a string anymore, but any object that can oscillate around a fixed point.
Exactly. The main difference is that how the mass is distributed in that object plays a big role in how it oscillates.
So the shape and size of the object actually affect how it swings.
Precisely. Calculating the exact time period for a compound pendulum gets a bit trickier, but the underlying principle of SHM still applies.
That's fascinating. It's like SHM is this hidden code governing so many different types of motion, from simple pendulums to these more complex swinging objects.
And let's not forget another interesting example of angular SHM, the torsional oscillator.
Okay, torsional sounds a bit intimidating. Can you break that down for me?
Think of it as a system that exhibits angular SHM because of a twisting force, or torque. Imagine a disc attached to a wire. When you twist the disc and let it go, it oscillates back and forth, trying to unwind itself.
So instead of stretching and compressing like a spring, it's twisting and untwisting.
Precisely. And the properties of the wire, like how stiff it is and how long it is, determine how fast the disc oscillates.
So the wire is resisting the twisting, trying to bring the disc back to its original position.
You got it. And that interplay between the twisting force and the wire's resistance is what drives those oscillations. It's like the wire is trying to untwist itself and get back to its relaxed state.
It's almost like a spring, but with a twist, literally.
Exactly. And just like with our spring and pendulum, the properties of that wire determine how quickly those oscillations happen.
Wow, we've covered so much ground today, from swinging pendulums to twisting oscillators. It's incredible how this seemingly simple concept of SHM shows up in so many different forms.
And we've really only just skimmed the surface. There are countless other examples of SHM all around us, from the vibrations of molecules to even, believe it or not, the swaying of buildings in an earthquake.
It's like SHM is this hidden language woven into the fabric of the universe. It governs how everything moves, from the tiniest particles to the largest structures.
You've got it. And by understanding this language, we gain the power to predict and explain a huge amount of what we see happening in the natural world.
So this isn't just some cool physics concept tucked away in textbooks, right? It has actual real-world applications.
Oh, absolutely. Understanding SHM is crucial in so many fields. Think about engineering, physics, music, even medicine.
Wow, that's a pretty broad range. What are some specific examples?
Well, engineers use SHM principles to design bridges, buildings, and other structures that can withstand vibrations and oscillations.
So they're using it to make sure things don't fall apart when forces are acting on them.
Precisely. And physicists use SHM to study how atoms and molecules behave at their most fundamental levels.
It's amazing how this one concept connects to so many different things. What about music? How does SHM play a role there?
Well, music is essentially all about vibrations and sound waves. Musicians and instrument makers use SHM to understand how sound is produced, how different notes are created, and how instruments can be tuned to produce those beautiful harmonies.
It's like SHM is the underlying rhythm of music itself.
You could say that. And don't forget medicine. Medical professionals use SHM principles to understand things like heart rhythms and brain waves, which are essentially electrical oscillations.
It's like we've been talking about this abstract concept, but it's really woven into so many aspects of our lives and the world around us.
Absolutely. And the more we learn about it, the more we can appreciate its elegance and its power to explain the universe around us.
I'm starting to see SHM everywhere now. It's like we've unlocked a secret code and suddenly all these hidden patterns and rhythms are revealed.
That's the beauty of learning and exploring new ideas. It opens up entirely new ways of looking at the world.
Okay, before we wrap up this incredible deep dive, is there one last thought-provoking question you'd leave our listeners with? Something that will keep them thinking about the wonders of SHM even after we're done.
I'd ask them to consider the concept of resonance.
Resonance. Okay, tell me more.
Have you ever noticed how if you push someone on a swing at just the right moment, they swing higher and higher?
Yeah, of course. It's like finding that perfect rhythm where a small push creates a big motion.
That's resonance in action. You're matching the frequency of your pushes to the natural frequency of the swing, and this causes the amplitude of the swing to increase.
Ah, I see. So it's about finding that sweet spot that amplifies the motion.
Exactly. This principle applies to all sorts of things, from musical instruments to bridges, and even to how our ears vibrate in response to sound waves.
Wow, that's amazing. It's like finding the hidden harmony in a system.
Precisely. I encourage our listeners to look for examples of resonance in their everyday lives. Look for systems that respond dramatically to specific frequencies, and consider how SHM might be at play behind the scenes.
I love that challenge. It's like a treasure hunt for the hidden rhythms of the universe.
Exactly. And that's what makes physics so fascinating. There's always more to discover and explore.
It really is. It makes you realize that physics isn't just equations and formulas. It's a way of understanding the world around us.
Exactly. It's about finding those hidden connections and appreciating the elegance of how things work.
Well said. We've journeyed far in this deep dive, from the basic principles of SHM to its incredible applications in the real world.
It's been quite a journey, exploring the intricate dance of periodic motion and the surprising simplicity of SHM.
I hope our listeners are leaving today feeling a little more energized and maybe even inspired to see the world with a fresh perspective. appreciating those hidden rhythms and patterns.
I hope so too. There's a certain beauty in understanding how things mood and oscillate, whether it's a tiny atom or a giant skyscraper.
Absolutely. And who knows, maybe this deep dive will spark someone's curiosity to learn even more about the fascinating world of physics.
You never know where that spark of curiosity might lead. It could be the start of an amazing journey of discovery.
Well said. Until next time, keep those minds oscillating and those curiosity gears turning.